In the early 20th century, physics faced a profound crisis. The laws that had governed science since Isaac Newton suddenly began to fail. Experiments with atoms and light revealed a strange and deeply unsettling reality. Particles behaved like waves, objects existed in multiple states at once, and observation itself appeared to influence physical outcomes. The theory that emerged to explain this phenomena became known as quantum mechanics. But quantum mechanics did more than revolutionize physics. It shook the foundations of philosophy itself. It forced scientists and philosophers to ask, what is reality? Do physical systems exist independently of observation? Is the universe fundamentally deterministic or governed by probability? To understand the philosophical significance of quantum mechanics, we must begin with a simple experiment. One of the most famous experiments in physics is the double-slit experiment. The setup is simple. Particles such as electrons or photons are fired at a barrier containing two narrow slits. Behind the barrier is a screen that records where the particles land. If particles behave like tiny bullets, we would expect two bands on the screen. But instead something remarkable happens, an interference pattern. The same pattern produced by waves interacting with each other. This suggests something astonishing. Each particle behaves like a wave that passes through both slits simultaneously, but the mystery deepens. If scientists place a detector at the slits to observe which path the particle takes, then the interference pattern disappears. The particle suddenly behaves like a classical object again. Observation appears to change reality. The origins of quantum theory began with Max Planck in 1900. Planck discovered that energy is not continuous. Instead, it comes in discrete packets called quanta. Later, Niels Bohr proposed that electrons orbit atoms in discrete energy levels. But the full mathematical theory emerged in the 1920s. Two key figures were Werner Heisenberg and Erwin Schrödinger. Heisenberg developed matrix mechanics. Schrödinger developed wave mechanics. Though very different mathematically, both describe the same quantum reality. At the heart of Schrödinger's theory was the wave function. The wave function describes all possible states of a system. But crucially, it does not tell us exactly what will happen. Instead, it gives probabilities. In 1927, Heisenberg discovered one of the most important principles in quantum theory, the uncertainty principle. It states that certain properties of a particle cannot be known simultaneously with perfect precision. For example, position and momentum. The more precisely we measure one, the less precisely we can know of the other. This is not a limitation of measurement technology. It is a fundamental property of nature. Quantum mechanics suggests that reality itself is inherently uncertain. The dominant interpretation of quantum mechanics became known as the Copenhagen interpretation. It was largely developed by Niels Bohr and Werner Heisenberg. According to this interpretation, quantum systems exist in superpositions of multiple states. The wave function describes these possibilities, and measurement causes the wave function to collapse into a definite state. Before observation, the system does not possess definite properties. Instead, it exists in a cloud of probabilities. Only measurement produces a concrete outcome. This leads to a striking philosophical conclusion. Reality may not be fully determined until it's observed. Not everyone accepted this interpretation. One of the most famous critics was Albert Einstein. Einstein believed that quantum mechanics was incomplete. He famously objected God does not play dice with the universe. In 1935, Einstein and his colleagues proposed the EPR paradox. They argued that quantum mechanics allows entangled particles to influence each other instantly across large distances. This seemed to violate the principle of locality. Einstein called it spooky action at a distance. This debate between Einstein and Bohr became one of the greatest philosophical debates in the history of science. For decades, the Einstein-Bohr debate remained unresolved. Then in 1964, John Stuart Bell proved a remarkable theorem. Bell showed that if Einstein's idea of local hidden variables were correct, certain statistical patterns must appear in experiments. Quantum mechanics predicted different results. Experiments performed in the 1970s and 1980s confirmed the predictions of quantum mechanics. The universe appears to violate classical notions of locality. Entangled particles truly behave in ways Einstein considered impossible. Quantum mechanics remains one of the most philosophically controversial theories in science. Several interpretations attempt to explain its meaning. The Copenhagen interpretation: reality is fundamentally probabilistic, measurement collapses the wave function. Many worlds interpretation, proposed by Hugh Everett III. Instead of wave function collapse, every possible outcome occurs in separate parallel universes. Hidden variable theories, proposed by David Bohm. Particles possess definite properties guided by a hidden quantum field. Each interpretation attempts to answer the same question: what does quantum mechanics actually describe? Quantum mechanics forces us to confront unsettling possibilities. Perhaps reality is fundamentally probabilistic. Observation plays a role in physical events, and the universe contains countless parallel worlds. Or perhaps quantum theory is still incomplete. Unlike earlier scientific revolutions, quantum mechanics did not simply replace one worldview with another. Instead, it left us with a theory that works perfectly but remains conceptually mysterious. Quantum mechanics is the most successful scientific theory ever developed. It explains atomic structure, chemistry, semiconductors, lasers, and modern electronics, yet its philosophical meaning remains unresolved. Even today, physicists debate what quantum mechanics truly says about reality. Is the universe deterministic? Do multiple worlds exist? Does observation shape reality? These questions lead us to one of the most fascinating areas in modern philosophy of physics.